it will not depend on past input actually, or it's independent of time. Like for example,
Fine.
uh, if a system has behaved in some way at past, t is equal to t minus delta t, so the
Mm.
response of the system will not be like dependent on the time actually.
Mm.
So the coefficient will remain constant for the ODE. So
Okay. Mm-hmm.
if I, it's like kx is equal to mx double dot plus kx plus t. So this m, k, and t or
Okay.
c, it will not
Mm.
depend on time actually. It will be constant coefficients actually, sir.
Okay.
Mathematically.
The implication is constant coefficient, but on the governing equation, you are right. But time invariance means, let's say I give the same input now, and I give the same input, let's say tomorrow. The system output should be the same, right? Fundamentally, that's the definition of time invariance, right? So consequently, the implication is that, like, when you consider the governing order in differential equation, the coefficients will all be constants, right? That is the definition of time invariance. So even if we consider the steering application, obviously the steering system is not going to be a time invariant system in real life, right? Because as we keep on operating, maybe today I operate a car, new car, it will behave in a certain manner. Let's say I keep on driving it for 1 year, right, due to some wear and tear and so on. 1 year later, I give the same steering wheel angle input on the same road under the same condition, the response may be slightly different. Okay. But then still we use the approximation of time invariance in our analysis. What is causality?
The system behavior doesn't depend on the future. It depends only on the past and the present conditions.
Correct. A causal system response means the system response depends only on past and current inputs. Okay, so it doesn't depend on probable future inputs, right? So that's something which we need to remember. So that means a causal system is non-anticipative. Okay, it doesn't anticipate what's going to come in the future. Okay, so this is the class of systems under study. Okay, and consequently, the mathematical model for this class of systems take the form of linear ODEs with constant coefficients. Okay, so that's something which you and I already know. So in vehicle dynamics, we would have studied the first two problems, right? That is, we are given a certain input and output. We want to get the mathematical model or the mapping, yes, right? So that is what is called as a model synthesis, yes. And we would also done prediction or analysis problem. That is, given various inputs, right? How do we get the corresponding output, right? So given S and U, how do we find Y, right? So this is what we would have done predominantly in vehicle dynamics, right? Let it be acceleration or braking or cornering and so on, right? So we would have solved the problem of synthesis and analysis or prediction, right? But in this particular course, okay, we are going to this problem of control. Okay, so that is you and I want a certain response Y or certain output Y. We know the system. The question is, what is the input U, right, which will get me that output Y. Okay, so that is what is meant by control. And in this course on control of automotive systems, that is the problem which we are going to be focusing upon. Okay, and we are going to essentially look at what is called as a concept of feedback. Okay, so and what is this concept of feedback? Before we go into that, let me sort of like draw this a scope of this particular course from another perspective. So if you look at control systems at a very broad level, depending on whether we have feedback or not, right? We have what two loop control. One is what is called closed loop control, right? So for example, let us say we have our ceiling fan, right? And then we quote unquote control the ceiling fan, right? How do you and I control the speed of the ceiling fan?
By varying the current, sir, through
By
a
varying the current.
right,
Exactly. But how do we vary the current?
using a potentiometer or knob actually, which will like varying the resistance actually in that sense.
Yeah. So we are basically using a regulator, right? A fan regulator. Let's say there are 4 speed settings. You and I will be adjusting the speed setting, which is factory calibrated, and then like depending on what we want, we adjust it, right? So that is a very simple solution, right? Where we are controlling, because let's say I want my fan to go at 100 RPM. I a corresponding speed setting of 4 in my factory. When I design and manufacture, I ensure that when I turn my knob to 4, it rotates at 100 RPM. Okay, so it's very simple. It's less expensive and so on, right? But what is the problem? Let us say there is some voltage fluctuation, right? Then what will happen? The speed of the fan will vary. Suppose, let us say I add some inertia to the fan. Let us say tomorrow I attach some weight or some other contraption to the ceiling fan. What's going to happen is that the rotational inertia of the fan will increase. So all those come in as disturbances and system uncertainties and so on, right? Then what will happen? If I set the speed setting as 4, end up rotating at the same RPM as 100 as before. So the problem with open loop control is that since there is no feedback, since there is no perception of what is the actual output at this instant of time, there is no way you and I can verify and take corrective action if required. Okay, that is a limitation of open loop control where there is no feedback. On the other hand, let us say there is an industrial application where I want the fan to be operated at a very accurate speed, right, of let's say 100 RPM. Then what do? I put in a speed sensor, I measure the actual RPM, and then I compare it with what I design. Let's say it's 100 RPM. If there is an error, I take corrective action. So this process of measuring the variables that you and I want to control and taking corrective action based on that as and when required is what is called as feedback. And we use feedback to design what is called as a closed loop control system. Okay, so that's the complement of an open loop control system. So in an open loop control system, since there's no feedback, we will not be able to account for any uncertainties or disturbances and so on, right? But in a closed loop control system, we have feedback and we should be able to account for uncertainty and system disturbances, right? Okay. So this is a very important block diagram, right, as far as the closed loop feedback control system is concerned. So let me draw it in a certain way. I will redraw it and then we will discuss it. Okay. So let's say we first start from the system of the plant. Sorry. Okay. So let's say, we have an electric vehicle and then we want to essentially, control the speed of the vehicle, so consequently I have an electric powertrain to which, let's say I give a voltage input and then that essentially controls my RPM, right? When essentially the wheel is traveling under certain load. Okay, so that's my system for the sake of argument, right? So we take that as an illustration. So a traction motor. So we have the system of the plant, we have the input and the output, right? Let's say I want my vehicle to go at 60 kilometers per hour. So then what am I telling is that I'm giving a desired output, okay, which we call as a reference input R of t. Okay, although it's called as an input R, why is it called an input R? We will shortly realize it. Okay, so it is a reference input. Okay, so by reference input, you and I are telling the system or the controller what is the value of the output that I desire or I want. Okay, So let us say I want the vehicle to go at a speed of 60 kilometers per hour. Then what I do, I measure the actual speed. Let's say it's 50 kilometers per hour. So, and then I give feedback. Okay, so this process is what is called feedback. Okay, so I feedback the actual speed. And then when I subtract the actual speed from the reference input, I get what is called as an error E of t between the reference input, which is the desired output, and the actual output. And then I take this error E, which in this case, let's say it's 10 kilometers per hour. And then I pass it through a controller, which will then calculate what should be the input that I should give to my motor. Okay. Then this input U of t is what is called as a control input. So you can observe how I drew the diagram, right? So initially, when there is no feedback, no loop, we just call U of t to be input. But when a controller calculates that input and provides it, essentially, when a controller calculates that input and then provides it to the system, that same input, is known as the control input. Okay. I hope this fundamental block diagram is clear. So this is what is called closed loop control system with negative feedback. Why is it called negative feedback? Because in this comparator, we typically subtract the reference input and the output, which is what is by and large done. Okay, so that is what is called as negative feedback. On the other hand, if in some cases, due to some sign manipulations, let's say we end up adding the two signals, right, to take the difference, we have what is called as a positive feedback. But that's going to be very rare. Okay, so to the best of my knowledge, we typically use negative feedback, but we should be aware of these two. Okay, the definition of negative feedback and positive feedback. Okay, now if we look at this particular feedback path, okay, so this path is what is called as a forward path. Okay, where we go from the controller to the system and the output and so on. And then this path is what is called as a feedback path. That is where we take measurement of the output that we want to control, and then we take corrective action. So sometimes what happens is that in the feedback path, there may be a non-unity mapping. So what do I mean by that? Let's say you and I want to control speed, but then I have only an accelerometer to measure the acceleration. Okay. However, what will happen is that I measure acceleration, but then I want to control speed, right? So I need to get the speed from the acceleration, right, to compare it with my reference input. So then what do I do to get acceleration, velocity from acceleration? So how do we get velocity from acceleration?
Integrating, sir.
We integrate it, right? So
Yes, sir.
we integrate it, we will get velocity. So consequently, we will get velocity, once we integrate the acceleration. And consequently, you will see that there will be a non-unity mapping, okay, in the feedback path. That is what is called as non-unity feedback. On the other hand, if there is no mapping, let's say we want to control speed, okay, and then we want to essentially we essentially have the speed itself as the measurement, right? And then we give it as a feedback signal to the reference input and directly subtract it. Then we have what is called unity feedback. That means we don't have any other mapping in the feedback path. Okay, the mapping in the feedback path is 1. Okay, so this is the difference between non-unity feedback and unity feedback. Okay, and what is meant by negative feedback and positive feedback. And overall, this is the closed loop control system with negative feedback. This is what is called as a forward path. This is what is called as a feedback path. Okay, so these are all important terms that you and I need to understand. Now, there are two more elements which I want to point out, right? So, in addition to system, controller, and so on, right? And the mapping in the feedback part. So typically, let's say, once again, we will stay with the example of, let's say, speed control, right? So suppose, let us say I have some sensor to measure the speed, right? The question is whether I will get an instantaneous response of speed, right? Very unlikely. Suppose, let's say the vehicle is going at 50 kilometers per hour, and suddenly the vehicle speed changes to 40 kilometers per hour, right? The question is, how soon will I be able to perceive that, right? Because the sensor itself, right? Let's say I may have a speed sensor. The sensor itself may have some dynamic response. Okay. Then the question becomes, will the sensor dynamics become important, right? In the overall control design, all right? So that's a question we may need to ask, and that may include a corresponding mapping or a transfer function in the feedback part. Okay, so we need to be aware of sensor dynamics. Similarly, let us say, I know that there is a speed difference. I know that I have to adjust the voltage given to the motor. Then, the controller calculates a voltage change. But then the question is, how soon can I implement the voltage change through some electronic circuitry? Okay, so that is what is called as dynamics of an actuator. Okay, so how fast would I be able to have an actuator which will implement the control input that you and I desire? Okay, so the actuator dynamics also becomes important. Suppose, let us say we have a system or a plant, whose time constant is of the order of, let's say, 1 second, right? But the actuator and the sensor respond in the order of 10 milliseconds. Then you and I can say, hey, look, compared to the system response of 1 second, the response time of actuator and sensor, which is 10 milliseconds, is very small. So consequently, we can neglect sensor dynamics and actuator dynamics. Okay. On the other hand, let us say the system response is of the order of 1 second, and the actuator and sensor also respond in the order of 1 second, right? Then you and I need to consider the actuator dynamics and sensor dynamics in our control design process. Okay, so that's how we keep on adding blocks in this overall block diagram. Okay, and adding, if we want to add some more items, we can also have disturbances coming into the system, right? So we may have unforeseen circumstances, coming into the coming and affecting the system response. You and I need to be prepared for that, right? Okay. So this overall problem, where we want to control the output of the system around a reference input, right, by adjusting the control input to the system, is what is called as an output regulation problem. Okay, why is it called output regulation problem? Because we are regulating the system output to a desired value, what we call as a reference input. And if we draw a big block diagram around the entire thing, okay, this entire thing, so you can immediately see that for this big block diagram, the what we call as a closed loop system, the input is the reference input, R of t, and the output is the actual output, Y of t. So now I hope it's clear why we call R of t as a reference input. Okay, because if you look at the overall block diagram, the closed loop system, right, we are essentially having we are having R of t to be an input to the overall block diagram. Okay, so that's why we are having this particular terminology, okay, for R. Okay, so I hope it's clear, right? Okay, so now this is where we would have this is what we would have essentially covered in the first video. So we would have just had a very broad understanding of the overall control design problem, and we would have just studied about what is called as open loop control and closed loop control, and gone through this block diagram, so that we can get an idea, right, about this particular topic. Okay. So now let's discuss questions on this before we wind up today's session. Okay. Yeah. Any questions on what we learned in this particular class?
Sir, I have a query. This is regarding that reference input.
Mhm.
So basically, suppose we are having a cruise control system in the car for timing. Now, for the reference input also,
Hmm.
while we're setting, suppose the car should move at around 60 kmph per 60 kmph.
Okay.
Now, speed has to be measured by some sensor as well, right, sir?
Mhm.
And even the control, like if you are deviating from the 60 kmph,
Hmm.
then the deviation of the speed also to be measured by some feedback sensor. Now, typically for the reference input and the control input, or I would say feedback input, do we have a different sensor or same sensor can be used for like deciding these parameters? I'm a bit I
Yeah.
just wanted clarity on this.
So reference input is something the user provides. Okay. So there is no sensor for reference input. Okay. So see, for example, let me take another example. Let's say we have an air conditioning system in our room, right? What do you and I do when we turn on the air conditioner? Let's say we have a split AC, right? We turn on the remote. What do you and I do? No.
Yes, sir. Yes, sir. I could like imagine now.
We give a desired temperature, right? So we say 25 degrees or 26 degrees or something like that, right? Correct. So that is something which you and I are specifying, Roshan, right? So essentially, we tell what the output should be, okay? And then what happens is that the actual output is measured by some temperature sensor, okay? Or in this case, the actual room temperature, right? That is Y of t. Then what we do is that we know we have a sensor to measure the actual temperature. The user provides the reference input, and then it's subtracted to get the error, okay, which then goes to the controller, and the controller takes action. Okay, so I hope now it's clear, right? How this works.
Right, sir. Thank you.
Okay. So once again, please note, although the term reference input has the word input, you and I are essentially telling what should be the desired value of the system output, okay, as far as the output regulation problem is concerned, right? So, and I have also explained why it's called input, right? So that explanation is from here, right? So if you consider the entire closed loop system as a block, R of t is an input to the block, okay? So that's why it's called as a reference input. All right, any other questions? No. Okay, so I hope as we progress in our lectures, I'm sure questions will come like last time, because I thought the flipped classroom learning, which we did for vehicle dynamics, was pretty, I think good for all of us, right? Because it allowed more time for discussion rather than just writing and one-way conversation. So we will try out the same philosophy this course also, right? As we go forward in the lectures, I'm sure there'll be more questions and discussion. Okay, today is only the start,
Sir, one more question I want to ask you. I'm sorry,
Yes.
it's a silly question, but sir, you mentioned that the positive feedback system is rare in this, like I would say, in application in that way. But there must be some, I would say, practical feedback system where positive feedback would have been required. So, do we have any such examples, sir, where just for understanding where it is used?
I have to search for it, Roshan. Okay, so to be very honest, I have not encountered it. Okay, so let me be very careful. Okay, so there may be applications where it is useful, but I have not encountered it. But it is my duty to teach you both. Okay, so that in future, if we encounter, we will know what to do. All right? Yeah, that's it.
Okay, sir. Thank you.
Yeah. So if any of you encounter a positive feedback example in your automotive application, kindly do let me know. Okay, see, we should not play with just mathematics to create positive feedback. Okay, so it is just very easy to multiply a sensor signal by -1 and make negative feedback as positive feedback, and as we will realize later. It should happen naturally. That's what I meant. Okay, so it should naturally lead to positive feedback. I know if you encounter such an example, kindly let me know. Okay. All right. Any other questions? No. I think your batch is strangely silent. You know, like I think I never had such little questions from your batch in vehicle dynamics.
Sir, am I audible?
Okay.
Sir,
Yes, please. No.
yeah.
I think the first video is very clear, sir. Going forward, we'll have some questions for sure.
Okay. Yeah, I think that's what I could also guess, because first video is just only an introductory thing, right? Yeah. So consequently, number of things would be low, right? Yeah. Okay. So then, if there are no further questions, let me take attendance. So 1 minute. Let me do the names. 1 minute. So I hope my screen is visible. No, sorry.
Yes, sir.
Yes, sir.
So let me read out the names. So previously, I was just projecting from the tab, so that's why I had to turn off my video. So I will turn on my video from the desktop. So Aditya,
Present, sir.
Anand,
Present, sir.
Anand Kumar,
Present, sir.
Arunachalam,
Present, sir.
Hassan,
Present, sir.
Hemant,
Present, sir.
Jagan. Jagan?
Yes, present, sir.
Kesav,
Yes, sir.
Lakshmi Narayanan,
Present, sir.
Prabhakaran,
Present, sir.
Prem.
Present, sir.
Okay, Prem is around. Okay. I think very rare that one class goes by without Prem's questions. Yeah. Prem and Roshan's questions. Okay, fine. Anyway, Roshan asked his share. I think Prem was silent today. So, yeah.
No, sir. I've gone through the videos, but there wasn't many.
No, I'm just joking.
I've already covered in vehicle dynamics.
Yeah. I'm just joking, Right. Rahul, no.
Yes, sir. Yeah.
Roshan,
Yes, sir.
Savish,
Present, sir.
Satish,
Present, sir.
Titus,
Present, sir.
Balish,
Yes, sir.
Vigneshwaran. Vigneshwaran? No.
Sir, is there? Is in travel? Is it travel that?
Okay. Vijay no. Vijay is that? No.
Present, sir.
Okay. Vikas,
Present, sir.
Vivekanand,
Present, sir.
Ramanand, Yadav,
Yes, present, sir.
Yuvraj.
Sir, Jagan here, sir. I'm present, sir. Sorry.
Yeah. I think everyone has marked as present, right? So I am also taking what our leader Arunachalam is telling. Like if he says someone is present, it's present. Yeah, that's it. Right? So I think everyone seems to be present. So we will continue our discussions tomorrow. Right? So as we progress during the class itself, I will give you homework problems like usual. Right? You need to solve them and then submit them. And we will also do maybe a couple of projects later in the semester, right? Once we learn enough theory. All right?
Yes.
Fine. Okay. Then we'll continue tomorrow evening at 5 p.m. Okay?
So any reference book to be studied, sir, in that sense, like for deeper.
So reference books, I will give you a few references on controls as we go along. Okay. So there's no single textbook as such. So just like vehicle dynamics, what I have done is that I have collated material from various sources, right? But I will give you some reference material as we go along, okay, for specific.
Sure, sir.
All right. Fine. Okay. Then we'll meet tomorrow at 5 p.m. Okay, and then continue. Kindly watch video 2 and then come back. Okay.
Sure, sir.
Sure, sir.
Thank you.
Thank you. Bye bye.
Thank you.